Hi everyone. The work I'm trying to present is a sort of combination of several projects I tried to accomplish, and we had this kickoff meeting in Boston months ago, where basically I stepped forward saying that I can look up for the AutoEncoder for the NANOAOD data here, and but I decided to provide additional update for the event classification because both topics sort of are connected, and I will go pick up necessary points in my slides to tell you what it's all about. Okay, hold on a sec. Just to give the brief overview what the NANOAOD means, because not everybody from the CMS. So we have this data format, which is basically should be centrally produced, designed for the analysis with the bare root, without additional CMS-specific classes on top of that the people should basically read it directly and can play with that. And it should have a relatively small size. Upon the discussion, it was discussed to have the size of the few kilobytes per event, but definitely it's probably subject to change. And eventually, when I will have the final data size, we'll see what's there. But basically, it should store the basic analysis objects and manipulate with the basic data types, such as integer, floats, etc. So it is what considered as a flat root tuple structure. So there is no nested classes, and especially there is no custom-based classes which inherit from the CMS-specific objects. So for those who are interested, I provide a link. So I will first start with the AutoEncoder, and for those who are not familiar what it is, basically this is a simple sketch. So it is an artificial network which composed by the two main components. One is called the encoder, which take the original input and project it into the compressed representation. Usually the compressed representation has a much smaller size than the original input. And then there is a decoder part, which basically take the compressed representation and represent the reconstructed input. As you can imagine, that the original input and the reconstructed input should be very close together, but not necessarily equal in whatever the metric you'd like to apply. But basically, the notion of the AutoEncoder try to compress the data representation and actually find out the dimensionality reduction, how to project the original data to the another domain phase space. So, oops, I'm sorry, wrong key. So the data representation in the root files, this is a very important topic. What we have in the root files is composed as a single NumPy array, which consists of two different branches. One, what's called the flat branches. For the flat branches, you have a single value per single event. For those, just to give you the example, for instance, number of neurons is resides in a flat branch because we have a fixed number. And then there is the jagged branches. The jagged arrays is basically the array of dynamic size, so it can change from event to event. For instance, when we talk about storing the electrons or neurons, we don't know a priori how many we have per event. So, and what we store is only the total number of these objects we have in the event. Therefore, their size will vary from event to event. And another dimension, which I will refer to, is the jagged dimensionality, because this represents the dimensionality of jagged arrays across all events you process. So if you have 2 electrons in one event, then you may have 10 electrons in another event, and the total dimensionality of the jagged arrays in this case would be 10 rather than 2. So what's interesting and interests me the most is how to project this structure to a machine learning algorithm. The problem is that mostly all of the machine learning algorithms which are available on the market right now deals with the fixed table-like structure. So the data are represented as a table where you have the fixed number of columns and the fixed number of rows. And this is not the case for the HEP in general. So in a sense, if you want to convert the HEP data to this table format, you basically need a two-step procedure, because first you need to find out the dimensionality of your data, and then you can construct necessary tables with this dimensionality. So the setup I used, I pick up the RealVal TT-bar NANOAOD sample, which consists of the 9,000 events. We have definitely more, but this is the file I played with. This file contains the 560 flat branches and 121 jagged branches. And their dimensionality, as you can see, varies significantly. So usually you need to transform the data to the suitable range which is acceptable and used by the machine learning algorithm. So in this case, I transformed the data to 0-1 range and applied the necessary pre-processing. And then I looked at the 3 different models, which is look for the simple autoencoder with different hidden layers, the deep autoencoder with 2 hidden layers and additional dropouts between the layers, and what's called the variational autoencoder with Latin variable space representation and a custom loss function. The training was done on the Tesla K40 with usual data splitting for the training, validation, and test sets. Originally I thought how the data should be transformed, and I found basically 2 different ways. The first one, which I refer as a vector representation, which is shown on this slide, you basically unwrap the jagged branches into the single NumPy array and add additional padding to the branches for in those events where you don't have this dimensionality. So at the bottom you can see the sketch I showed that the flat branches will be mapped directly, and then all of the jagged branches will have this padding in addition to the real values. So in order to start, just give you a few benchmarks. For this transformation, I've used the Jim uproot package and provide him quite a lot of feedback to fix different stuff. But it really works really well on the flatroot files. So as you can see, the rate which we read about it like 100 kilohertz our data, which is very nice. And we also try to read the data remotely through the XRD, and it also works fine. The large compression of the data, it is possible. So out of almost like 2,500 vector inputs, it can be compressed significantly with a 90% reduction factor. What is puzzling me is how to, what is a useful part of the compression and which boundaries we should apply to keep the output close enough to the input. So the training time can grow significantly depending on the number of parameters your model needs to deal with. And I just provide you a simple example of the variational autoencoder. So it consists of like 27 million parameters. But it still was able to train it in terms of like few minutes, I mean tenths of the minutes. So just to briefly describe what the variational autoencoder is. So it's a variant of the autoencoder which take additional step for your data. It basically takes the input representation, the mean vector of your values, along with the standard deviation, and it draws the events from this representation in order to build up the compressed representation. For those of you who are interested in finding more details, you can follow up the links. So when I applied this different autoencoders, the first thing to do is to look at the model loss through the number of epochs during the time when you train your data. And even though I was pleased to see, especially in the case of the variational autoencoder, that the shape really nicely reproduce the expectation how you should see your losses, definitely there is a question, should we trust the results? And for that purpose, I look at the different distribution of the variables I'm taking in and look how they are decoded back from the autoencoder. So in this particular case, you see the electron PT distribution, and on the bottom, two plots demonstrate how simple autoencoder decoded back this input and how variational autoencoder decoded back this input. As you can see, basically the simple autoencoder doesn't have a clue about the shape of the distribution, while in the case of the variational autoencoder, so it tries hard to get closer to the distribution. What's interesting, of course, that it is the decoded variable significantly depends on the choice of your input distribution you put into the variational autoencoder. So for instance, for those distributions which are mostly uniform, then the variational autoencoder doesn't really do a good job because I didn't feed this distribution directly for this particular subpart of the attributes. For others, it's actually doing quite good job. For instance, here the jet mass distribution, and you can see that the errors, basically those the residuals, which are very, very small in this case, and the peak on the top right distribution, which is a decoded part, correspond to the padded values, which I added to the my original distribution. So another approach to try out is actually transform
This is Mike.
Yeah.
Can you go back to the last page and maybe interpret what you're seeing a little bit more detail?
Okay.
Because
so,
what I see is that the jet mass on the left, top left, and the jet mass distribution at the top right don't particularly look like each other. They peak in different places.
That's right. So the point here, so let me come back a little bit to this pictorial sketch of the variational autoencoder. So here, the mean vector, you need to supply a distribution which you think your data will follow. And I tried the different inputs, like I tried the uniform, I tried the Gaussian, and I tried all of this different stuff. And depending on your input, this is how your output will looks like, actually. And this is what this distribution, this slide for the electron PT and this slide for the jet mass, they comes from the Gaussian distribution, which I put into the variational autoencoder. The point, you're definitely correct that the distribution is shifted. The problem here is that I'm not fitting a single distribution. All of the jagged arrays branches, they have different distributions, while I applied to the variational autoencoder a single distribution which represents my data. And this, my understanding, affect the final outcome. And that's one of my conclusions.
What is the loss function? Is it the absolute difference between the two, or the
No, the
relative
loss
difference?
function is, I mentioned it here, it's called the Kullback-Leibler divergence. And I pick it from whatever the paper they supply.
Wait, but you have you mean in the variational autoencoder, but you have two different components, I think. You have the
those are two different
loss, and you have the other term, I think. Yes. So
yes,
for the reconstruction loss, do you use the absolute or some kind of relative error?
No, it's an absolute error.
Okay, so but I'm just wondering if then you get better performance, a better agreement at higher values of the variable than at lower variables, for example.
That's also a true statement. And because of this variety of the input parameters, I definitely try to play and see how the data will look like at the end without definitely a priori knowledge which one would look best. And it seems to me it actually would be the input dependent rather than independent. Of course, you want to find out what independent parameter you need to put. For instance, if you take the absolute error as your initial metric, then I hope I will apply this not only to the TT bar, but to another sample. But I don't know if that's going to work.
Okay.
But for instance, in some sense, you might think that if you've got if you've parameterized the errors for the electron, I don't know if it's some dp over p plus or some energy thing that comes from the calorimeter, you know roughly what your true sigma should be for an electron at that particular PT or whatever, right? And you could use that.
That's right. So what I'm saying that the code I developed, and it's actually quite new code to me. I'm not really full expert on this yet. So far, it accepts only the single input distribution, but probably what we need is actually feed to the variational autoencoder the different distribution which will project to our attributes like electron PT or eta or any other attribute we'd like to encode through the autoencoder. And that's, I don't know if anybody yet done that. What I've looked in the literature is only how people use a single distribution to describe the entire data set. Okay, any other questions before I'll move on? Okay, seems not. So I'm whatever the slide 14. Another idea which I was trying to explore, and actually this is quite neat idea. Several people, as far as I remember, it was the PhD thesis on Atlas, showing that a different approach that you can represent our HEP event as an image in some phase space, for instance, in eta phi space. And in this case, you don't need padding. So what you have, you need to have this the phi eta space matrix where individual cell will contain a branch vector of your jagged arrays. The problem with this approach, though, that you may choose the granularity of your matrix such a way that different particles will overlap with each other. For instance, in one particular slot, it may be feasible to put, let's say, electron in a jet. And this definitely only depends on the granularity of this matrix, but the granularity of the matrix significantly impacts the training time. So this is the slide I'm outlining the challenges of this approach. For the data transformation with a padding vector, one of the challenges which I did not know what to do with is what to choose as a padding value. So in my case, I tried 0 and -1 just to distinguish these values from the real actual values of the jagged arrays, but it can be any number. It doesn't really, there is no constraint what to choose. Actually, if I choose this padding value, it may affect my distribution because it creates a bin with the padded values, which skew the distribution one way or another. The largest dimensionality of the jagged arrays across the events or physics samples is also the issue, because if I choose, for instance, the jagged dimensionality for the TT bar sample, I cannot apply it directly to the J side sample because those will have the different representation. And for the matrix representation, what I found, as I claimed, that granularity of the single pixel on your picture really can cast two values in one. And I don't know what to do in this case either. So plus the, if you choose, for instance, the 100 by 100 space matrix for the eta 5, it already creates 1 million parameters, which significantly affect the training time. So just to give you the idea, I was able to run the vector representation in terms of few minutes, I mean like 10 or half an hour in this case. But for the matrix, when I supply this 1 million parameters as my matrix, the training time runs for at least a week. And definitely the 100 by 100 representation of the matrix is nothing. We need more finer granularity for that. So, and my outcome from this study is that if we know the correct distribution, then probably the padding vector approach will work. But then in this case, we need to feed this distribution to the autoencoder in order to help him to identify how the data input looks like. So to summarize this part, I tried 2 different approaches and I outlined the challenges. What I also trying to investigate now, how to apply another type of network, which called the generative adversarial networks, which basically learn any data representation. For those of you who heard these talks from the DeepMind, who are training the network to learn these Atari games, these guys use the generative adversarial networks. So, and I only come up with a code this week just to see if it's gonna work. So I'm quite interested to look at this stuff as well. For the matrix approach, I'll be interested to pursue, but probably I need larger resources than I have in order to reduce the training time. Because when I ran this single round for the 1 million parameters, the output of this 1 week training was not that great with respect to the vector representation. But I think what we actually need in order to deal with jagged representation, we need a dynamic layer for the neural network, which can take the jagged arrays, map it into the fixed size table representation, and then unwrap it back at the level of at the another end of the neural network. So I have some ideas how to deal this, but it's not yet crystal clear. So
Valentin?
Yeah.
Hi. Just about GANs in general, I'm not sure that that's applicable in this situation, because they just try to find any examples that fool your adversary. So it's not very good for like reconstructing the samples you want. They will just try to fool you in a sense. Just try to pick like the most generic examples that fool your adversary rather than helping you reconstruct the data. It's a similar thing for variation autoencoders. So I think both of these here are not as, I guess, useful for this case, because they're more useful for example, the task, give me an image of a cat that a human can't tell apart from from another cat image, rather than kind of being like, please reconstruct this image, which is what the vanilla autoencoder does.
But you could actually, if you successfully manage to reproduce it with the variational autoencoder, you could use it as a simulation based on data in principle.
Yes, you could. Yeah.
And then another comment actually on the generative adversarial networks. There was some time ago, some months ago, there was Ian Goodfellow. I think he basically invented these things at CERN, and he said these things can actually fail in bad ways, in the sense that, as the other person said, they basically try to generate something which you cannot distinguish from your underlying sample, but then there are some modes which basically they just always produce the same example, and then your discriminative network always says, oh yeah, it looks like the data, even though it's always the same. So I think in a nutshell, the GANs can be quite tricky to work with.
Okay, thanks a lot. So that's the reason why I want to get some feedback, because
I don't want to discourage you, but it can be tricky apparently. So.
I understand, but I'm definitely interested just to apply and see what will come out as a result, just to get some idea. And then
I think what's interesting about the GANs is the way that they can, ultimately they collapse the data down to this latent space, and that somehow is maybe what you want, because you've reduced the dimensionality of the data a lot, so you've achieved the compression. So if you could get it to the stage where you could split your data sample in two, train it on one, and then have the adversarial part try and distinguish between the real data which had gone through the compression and decompression state versus the data that hadn't done that and it was pristine in some way, then maybe that would be a useful way of directing the training. Because I think, as Mike said earlier on, what the VAE is showing, I mean, it looks okay, but it's not great at all.
Yeah,
so I think there is some promise there, but as you say, it's tricky. To avoid getting basically the same piece of data all the time is not what you want.
So Graham, you might know more about this than I do, or someone else here, but doesn't Atlas have a, I think it's Atlas, but maybe I'm wrong, is doing the CalO-GAN project to use these adversarial networks to train the fast simulation?
Yeah.
Yes.
Because that seems like it might be rather close to this in spirit.
Yeah, so I will follow up whenever we'll have the formal presentation. So I expect that.
David, also here, I'm pretty familiar with that. I think the big problem here is really what you call a JAG, the JAG array.
Yeah. So this is the most really problematic part, what we should do with this. I definitely have no clear idea about how to proceed with jagged arrays. I'm trying. What I'm saying, we can apply different ideas, but there is no clear path what we should do. And actually, to slightly give you a little bit of some, that maybe what we need for the autoencoder and compression, that we can look at certain distribution which compress well, and then combine this with like a flat distribution, which definitely will compress better than the jagged arrays. And this would be a halfway approach to find out the best variables which we can use for the compression.
Yes, a comment on what you call jagged. I think other people call it variable length or something. So if you look at, I mean, people typically use recurrent networks for this. I don't know how this would work in an autoencoder setting. So this would be something like, can you yes, and this is a lot used in machine translation and text analysis and natural language processing and things like this. It would probably be something like, can you translate English to some compressed format and translate it back and see if you get a difference? And another comment is, so there are some papers, I think, in Atlas where people have used this to do, I don't know actually, I think look at boosted tops or boosted W's or something. But then in CMS we have this deep CSV, and you would also think that the B-tagger is a good candidate for this. But I think what they ended up doing in the end is having fixed size input, but then they have the first one. The first layer, I think, is a 1D convolutional network, which is essentially saying that they have different variables going into the first layer, but then they repeat it for every track essentially or something. So this is maybe something you could get inspired by. So.
Yeah,
I don't know how they solve the padding. How they solve the. You mentioned have this problem. You don't know whether you should what you should do with the non-existing values. So I guess they just set things to 0, but I'm not sure. So maybe you can find some ideas there.
Can you send me the link? I would appreciate that, or at least some
yes,
pointers,
I
whatever
I can
necessary.
find the node or something. You're in CMS, so I can send you even links to internal nodes, I guess.
Yeah, sounds good.
Okay,
so my last comment on this, Valentin, is one that it's almost trivial, which is that I think the audience today is a bunch of physicists, and we're all very smart, but it might be useful to talk to some computer scientists about this.
Absolutely, and I think there would be more interesting to solve the jagged array problem than what that we're interested in, because for them, this is the real area for the research. The problem here, I think, we need to find out a similar use case outside of the HEP, which will have a similar problem. If you know, I don't know, right away what it looks like, I'll be interested to learn, because I'm trying to find out where else the jagged arrays are represented in data that we can use a similarity between the HEP and other domain in order to approach computer scientists to address this issue.
No, I think you've identified the key problems. I don't think they have a solution, which is what probably makes it interesting to them.
Translation is a usual problem. To translate the sentence never have the same number of words or verbal for speech. I mean, you never have the same number of phonemes. But I'm sorry, I think I missed the purpose of this study. You want to compress in terms of reducing the size on disk, or
yeah, so basically, so we'd like to find out if there is a compressed representation of the data which we can use in terms of the size.
Mm-hmm.
What should be compressed is unclear, so we just like to find out if there is a possibility to compress. And as I pointed out on a different slide, here the part in the second bullet, that if you consider the ratio between the flat and jagged data within the event, we have more jagged data than the flat. We can compress the flat, but actually it would be much more interesting if we'll be able to compress at least partially the jagged part.
Mm-hmm.
Because
you compress on an event basis, right? You try to compress every event. Okay.
So in this case, if you just do the simple math, right, if you talk about whatever, terabyte or petabyte, so then you can see how much out of this you can compress, because if you compress the flat part or jagged part, so it's two different scenarios.
Yeah, but I mean, the jagged part is flat in a different direction, right?
Yeah.
So maybe I'll wait to comment until Constantin talks, because you're basically going about this the opposite way that we're doing. But you know, like, yes, you have a different number of particles in every event, but you typically then store a fixed number of features per particle.
That's true.
So if you compress per particle, which is what we're looking at, then you don't run into this problem of jaggedness. But then also, thinking further down the line, calibrating with the data a per particle compression is easy, because you would just do it the same way you calibrate any particle ID, tag and probe or something. I don't know how you would calibrate an event level autoencoder, because I'm not sure how you would, how would you do a data-driven determination of the, the effect of compressing with this thing on one type of event when you've trained it on another. It's not clear exactly how you would actually use such a thing in a precision analysis. I
would agree with that statement, yes.
But if you compress per particle, it's straightforward, right? I mean, you just imagine you have, if you want to know what happens to muons as a function of PT and eta, you've got an infinite number of J side of mu, and you just make sure that you have uncompressed, some downscaled uncompressed sample, and you just look and see what it does.
Okay,
when you say per particle, you mean per type of particle or per individual particle?
Well, so for each reconstructed particle, you could compress it. Now, whether you can imagine different ways of doing that, whether you have a single encoder that just compresses any particle, or you have a different one that is meant to compress different types of particles. You could imagine doing either of those depending on what your data stream looks like. We haven't gone that far, and really, we've just done, Constantin's going to show, we just did the proof of principle of what if you just take a bunch of particle ID information and you just try to compress that. It's a fixed amount of information. A lot of it's correlated. Can you just, compress that down and blow it back up? And he'll show you that it seems like, yes, you can do that. But exactly what your final strategy would be, I think, would really depend on what, you experiment and the situation and things.
Because I think one potential problem with Valentin's approach may be that you have to get the weights right, so that the precision in jets, how is this weighted with respect to the precisions in electrons, for example, how well you reconstruct electrons, and so on. So this is something you have to probably think of.
Yep. Okay, so I'll move on to the second part for the event classification. Just to give you the idea, this is, again, a bunch of different ideas rather than the single project. But basically, can we do the event classification as an unsupervised problem? The idea was to start with a simple supervised use case to understand the formats, representation workflow, and then how to deal with the large data volumes we have in the continuous training. Then even try to use the AutoEncoder studies to understand if we can do some interesting data representation for this purpose. And there is a huge engineering problem, actually, how to organize the entire workflow that we need to able to provide the demonstrator to build the model self-predictions and stuff. So I've been start looking at the different types of the architecture, how to actually serve the machine learning or deep learning service via the REST APIs with a high efficient data transport layer. For instance, we can use the uproot as we demonstrate now that it can read the remote files. And then we can put on the A box the model trainer, which will read this file and continuously train the model. And then we may have an independent client, for instance, our reconstruction software, or just a client like a cool client, whatever, which can basically ask for this type of event, just give me the predictions, and I'm happy with that. So, for the event classification problem, I start looking into the idea of not using tracking at all. Can we reconstruct events just using our hits from the detector? Even though claiming that we don't need the tracking, of course, I understand the statement, but what I've done, I use the tracking itself, where I extract the hits from the tracks, and I only use these hits in order to classify the events. And the initial attempt using the convolutional neural networks. And the initial attempt was try to use 3 different samples, which represent the different physics events we're dealing with, JSI, QCD, and Higgs. And I used the XYZ Higgs coordinates in the global coordinate frame to construct the image, which is now exact PNG image. And I shown 3 projections in a single image. And then I decided, instead of building my own network, there is a nice framework which you can grab and try to use, which provide you world best CNN models for free. I mean, those are already pre-trained, and then we can start using them. And then I look at how to optimize the pipeline itself. So this is the typical events from the 3 different samples, and you can see here the top part is represented YZ plane of the hits. The middle one is XY, and bottom one is XZ planes. And the different colors corresponds to these pixel and silicon detectors hits. So, and I just grabbed these images and I put them into the 3 different network, and I try to classify, I mean, doing the similar job as we classify dogs versus cats, basically, or different type of breeds of dogs. And then, as you can see, just using out-of-the-stock convolutional network, I was able to achieve quite nice accuracy among the different samples. And then there are different tricks how to tune the network. So this is the last 2 columns, which show that I modified the ResNet 50 network, and it significantly improved the accuracy of the classification. So basically, the outcome of this that...
I'm sorry, Valentin, can we go back to that page? One quick question.
Absolutely. Yeah.
So this is the accuracy after some amount of training.
Yeah. So
do you believe that you have good reason to believe this is converged to its asymptotic value? Did you do this based on some finite number of iterations?
So what I've done...
Is this accuracy based on then a validation sample, a test sample?
Yes, this is the accuracy based on the validation sample, so it's not the training accuracy. So what I've done, I've picked the 10,000 events of each sample, I convert them to images, and then I use the standard procedure 70-30 splitting for the training and validation, and then I use the out-of-stock model. I literally took the model which was used for the dog breeds, and then I applied the labels for the samples. In this case, it was only 3 labels, and then I compare this model how it's done the classification on dog breeds, and then I run the same stuff how it trains HEP events, and this is the results. And in my images, haven't contained any track traces. It's only hits.
But in reality, you will not have the same number for each class, right?
Of course.
So
what I'm saying that I'm giving you exactly what I've done. What I see that the neural networks will be capable to use our hits in order to distinguish events with what will be the final outcome. We may take this as an initial stuff for our triggers, right? So we can classify single neon, double neon, or multi-jets events, or something like that. Pick up different samples for those trigger lines and compare how we can do this classification just using the hits.
Which extent the classifier does not classify on trivial things like the number of hits?
I'm not sure I understand the question.
I mean, there is different. If you just look at the picture, it's clear there is the number, the multiplicity, just the plain number of hits per event is different between the events. Then if you just use, okay, my tagging variable is number of hits, then how good would you work this very simple variable compared to what you're doing?
So you're saying that let's split this in terms of the number of hits per event and see, just base it on the number of hits per event, how the classifier will deal with this.
Yeah, because we have no, okay, it could be that it's in fact classifying on trivial thing rather than topology.
Okay, I can check that. So.
Right, I was thinking the same thing, that well, the kinds of events that are being compared here, things like Higgs versus J psi, it might be keying on the activity in the event rather than anything even approximating precise masses. Although it would be kind of synthetic, I think that this would have a very hard time distinguishing a 90 GeV Z boson from a 100 GeV Z boson if those were two events.
But as you can see, the Higgs versus QCD is still quite good. And if you look at the image representation of these two samples, they, I mean, visually you can claim they look alike.
Oh, okay. How
in
about
terms of multiplicity and stuff.
versus...
Jim, you are dropping a lot.
How about Higgs to B bar versus... general QCD doesn't have two B quarks in it, but there are a lot of such events, and that's what's difficult about finding the Higgs. So how about Higgs to BB bar versus Z to BB bar?
Yeah, I mean, I'm happy to look at this.
Yeah, if it can distinguish those two classes of events because they only differ in the mass of the BB bar pair, then that would be really a strong statement.
Yeah, absolutely. I mean, for me, it's just a toy. I'm enjoying to do this stuff because it's interesting by itself.
Right. I'm just trying to see if what these neural networks are doing is identifying activity in the event, which is a fairly easy thing to do without tracking. I mean, you could count hits or energy in the hemispheres or whatever, versus actually doing what a track fitting does and finding mass peaks and such. Because that would be...
So I definitely welcome all of these ideas. Just send me the note and I'll be happy, because now I've built the pipeline. That was a difficult part. It took me quite a lot. But now I don't need a sample with the cluster of hits. I can just pick up the normal sample with tracks. Now I can convert it back to the hits representation. That's the point. And then from these hits, I can just start doing the normal convolutional networks training.
Okay.
So I don't want to take more time, but basically the point is that I build a pipeline, and I'll be happy to continue with this as well. And so that's it, what I have. Sorry that it took longer than expected.
All right, thanks, Valentin. Given that we had a sort of bunch of inline questions and we're running a bit late, why don't we go on to Constantin's talk? Can you share your slides?
I'm not 100% sure how to do that. Give me a second.
There is this triangle button on the video. You can click and then you choose like a preview or whatever the application you are using for the slides.
Yeah, they're visible now.
Perfect. All right. Okay. So I'm going to be talking about AutoEncoders for LHCb, and unlike the previous talk, we're trying to compress on a particle level rather than the event level. The motivation is the classic one. We collect a lot of data, but our write-out is limited. And we know that many of our stored variables are very correlated. So we propose to use a vanilla rather than a variational or anything else autoencoder that compresses the data before writing it out and then decode the result when doing the analysis. That way we can do more physics. So this data set, this toy problem we're looking at right now is LHCb minimum bias Monte Carlo, and we extract equal numbers of electrons, muons, pions, kaons, and protons. And for each one of these, we have 9 PID variables. So each one of our tracks or particles has information of all of these 9 PID variables, so no missing data for now. And we expect these variables to be correlated. We will try to use an autoencoder to compress these variables. And to evaluate the performance, we will look at ROC curves.
You're compressing the 9 PID values only?
Yes, right now,
Okay.
this is only a proof of concept preliminary study. We're only using 9 PID variables because we know they should be correlated, and this was just a proof of concept. So let's see what happens. So we use a vanilla autoencoder with 3 hidden fully collected layers of 19 neurons each, so keeping it somewhat small because we only have 9 input features, and we vary the number of the compressed features in order to see how much compression we can actually get. In order to help the autoencoder learn, we scale the input features to be Gaussian shaped. And I wrote a little package that's linked here that does that for you. And so we use a loss function of the mean squared error in these scale features. And we use 70% of the data for training, 25% for validation, and 5% for test. Okay, so we will use ROC curve to see how well the compression has worked. You've seen ROC curves before, I'm sure. On the x-axis, we have the false positive rate. So, for example, if I label something as a muon, it actually is a muon. On the y-axis is the true positive rate. So I label something as a muon, and it actually is a muon. So the 9 PID variables that we have are traditionally used to cut on. For example, prob NNE is used as a variable that's cut on to select electrons. So I will show you the ROC curve for distinguishing this particle, so the electron, from all the others. So it's a one versus all others approach. And these are some of the results. So here, so we have 9 input features, and here we're compressing it, or basically not compressing it at all, to 9 features in the compressed representation. That means that if our autoencoder just remembers all of the 9 features we give it in the beginning, then the output should be exactly the same as the input. And that would mean that the ROC curves for the input and the output variables should be exactly the same. And that's represented in these graphs, in these for the 9 variables here, as the blue and the red curves, and they overlay basically completely. And that's what we expect. Okay, so now if we have, if we use 8 variables, so we compress the 9 features into 8 features, and then blow it up back out to 9 features, then we lose some information clearly. But because the input features are correlated, we can reduce without losing any relevant information, and that's how the autoencoder works. And we see that still the ROC curves for for the input and the output variables basically perfectly overlaid, so everything is fine. So now we can reduce this number of compressed dimension to 7, and it looks the same. 6, and it's still okay. 5, it's fine. 4, you can see a few differences. 3, you can see you can start to see some bigger differences, and that's a compression factor of 3, by the way. And if you go to a compressed dimension of 2, we really see we start to see bigger differences in more than one variable. And if you go to 1, the curves are significantly different. So basically, in summary, this is only a very preliminary study, but we've shown that autoencoders can be useful to compress the PID information in LHCb. And it depends on the use case that you have by what factor of compression you choose. But a factor of 3 compression in this case seems appropriate for this data set. I did not really tune the network very much, and I could add more training data. So this can be improved a lot. But I think the main point here is that this is a technique, and it has wide applicability to other variables and experiments, and it works and can really be used to help us compress data on a particle level. All right, so thank you.
So Constantin, this is Mike. So
yes.
This works very, super encouraging. I've got a couple quick questions. Did you use doubles or floats? And does the algorithm allow the possibility of storing data with a not a different number of words necessarily, but a lower level of precision, a lower number of bits?
I've used doubles so far, but I don't think, it's Keras, so if Keras provides that possibility, and I think it does, that should not be an issue.
Because I can imagine that there would be an additional ability to go, even if you started with doubles, to go to floats, or perhaps even to have floats for some of these, some of the stuff.
I guess whatever you want, yeah. Sure.
And we don't need floating point precision for the final prob NNE or whatever.
Yes. The other approach here would be to just reduce the number of dimensions in encoded dimensions anyways. So if you don't need as much information, you can keep fewer variables, or or you give them less precision, whatever you want.
I don't know what handles on precision for individual variables that these tools provide.
I'm not 100% sure either. I think there is something that you can do. I'm not 100% sure, but this is more of a proof of principle, and in terms of implementation, yeah.
And it's great. This is factor of 3 count.
Yeah.
Yeah, I had a question actually. So, so you get a factor of 3 in terms of the fact that you're just storing 1/3 of the amount of information. Now, when we store our data, of course, we always then put on top of that some lossless compression to try and just reduce the size on disk as much as possible. And I really wonder, it would be very interesting to see if you got as much lossless compression out of your 3 variables as you did from the original 9. Because somehow the information in those 3 must be more concentrated, in inverted commas. I think that would be certainly useful to look at, because ultimately that's probably what we would still do on disk.
Yeah, but I would add on top of that how to provide the benchmark comparison between any compressor algorithm you can apply and this autoencoder, just to compare between the two, how they deal with that.
Say again?
If let's say if you take the gzip and compress your events with that, and then you take the autoencoder and you achieve the factor of 3, how you compare the autoencoder versus gzip, which will compress all 9 variables?
No, I think you probably the benchmark to do would be, I mean, you would apply this technique and then run it through gzip compared to not using this technique and run it through gzip. So then you get the real, I mean, the real factor what you will save on disk essentially.
Sure.
But these are floats through gzip. They're not going to compress that much, right? The raw floats without any root buffer overhead, and I mean, you can.
Well,
you can
the fact that they're floats, you know, I think like to answer Mike's question, you know, there's no reason why you can't run this, take the compressed hidden layer, and then do some sort of bit packing to that, right? You just have to look and see what happens. So if I take these doubles or floats or whatever they are, and then I decide to bit pack them in the same way we kind of do things now, or we roughly know the precision, I just have to study what happens then if I go through the same process that we go through now and blow them back up, and then I run them back through the inverse compression and see if I caused any problems, right? I mean, in principle, it should be fine, but we'd have to look at it. It'll be also interesting, as you say, to look at see what happens when you try and take the features and further compress the thing that you've just whatever this thing is you've just made. Try to run it through standard compression tools.
Yeah.
I was wondering, have you also tried a simple linear principal component analysis to compare against?
I have not used PCA, but I mean, I can. I mean,
I guess it would be interesting. The day you write this up, maybe you want to compare against that also.
Yeah, I mean, I guess if you keep the problem very simple, they'll probably give you roughly the same answer. Although I think, you know, the ultimate goal here is that we wouldn't just have nine features that we know are quite related. We'll have 50 or 100 features per particle or something. So I would kind of suspect that the two diverge a bit as you make the problem more and more complicated, but
yes.
We could certainly give it a go. I mean, in this case, they should be similar because, I mean, he didn't actually talk about what these features are. The ones that are called PNN, I mean, this is a neural network that's trained with something like 20 or 30 features per particle. And the other features are the most powerful input feature to the neural network, which is effectively the traditional way of doing particle ID, where it's a likelihood-based feature that combines the likelihoods from all the different subsystems. So in this case, you would kind of expect that principal component, you could do something sensible. But when we go back to when we start adding more and more of the features that are related in very bizarre ways, and some of which have only looser correlations, I would kind of suspect the two approaches to maybe diverge a bit. But it's certainly something that'd be interesting to try.
I guess it would give you a baseline why you need some non-linearity essentially, just to demonstrate.
Yeah, definitely.
And the other nice thing about the AutoEncoder is you can just use the variables at the end just as you would otherwise. The problem with something like PCA is, yeah, you might select out of these 9 variables, you might be able to select also just 3 variables, like you cut out the rest and only keep like the 3 more complicated combined variables. But then it would be not as nice to do your analysis later, because then you can't just cut on, as we'd say, like prob mu or whatever, to select nuance.
Wait, no, but as far as understood, essentially, if you would not put any non-linearities in your neural network, you would have a PCA, essentially.
Right, so you would have to, in the PCA, you wouldn't just store the features, you would have to remember, in quotes, the relationship between the original ones.
Yes, here you have to remember your trained network is the same.
Yeah, no, I'm saying that the same. I'm telling Constantin that yeah, if it's
yeah, you guys are right.
Yeah, that is
makes
the same.
sense.
Okay, any last questions or comments for either talk?
This is Mike. So I've got one last comment. I'm impressed by both of these talks. I think it's really valuable work. And then the question comes, is there some way to engage with people from the computer science or the larger data science community? I don't have an answer for that. I just, think people should be considering that.
So, well, yeah, that's a constant debate, and we had another thread actually this morning about people saying, how about if we'll release the CMS raw data for the machine learning community? And from my experience, I worked with several students from the computer science and with a professor as well. They will not just take the data unless we'll provide all the tools and represent the data in the standard formats which the machine learning community expect. And I don't really, the people start arguing quite a lot that no, that's not the case, we need to release the data. Of course, that's all of these factors true, but if we need to gain the momentum and attract computer scientists, we need to project our problem to a problem outside of HEP. Then it would be much more interesting for them that it's not only just a HEP, we just have a bigger scale at stuff and probably more complexity, but it's still they can pick up a small sample and then assign a single problem to a student, but without manipulating, without representing our data in this format, it's become really hard to attract them. They don't want to waste their time struggling with our formats and our representations. They just need to use, normal MNIST tarball, whatever it is, or any other sample like that, and then they can start attack the problem. And if we expect that our data, but by just releasing our data, magically everybody will jump in and start helping us with the machine learning problem, I really doubt that's going to happen, unless we make a significantly change our mind and represent our sample in such a way that they will be attractive to the computer scientist.
But this is quite easy, right, for the per particle approach.
Well, yeah, so that's true, but it's really hard per event.
Right, but for us, like if our goal is to compress particles, putting the data in a format that anyone in the world can use is trivial because you have 5 or 6 types of particles, and then you pick the features, and you could even write a CSV file or something that has as many particles as you want with different properties.
That's a true statement. Yes, I agree.
Anything else from anyone? All right. Thanks, everybody. Apologies again for the room. If anybody tried to get in and found it locked, we'll figure that out better for next time. Thanks, everybody. Have a nice evening.
Bye.
Thanks very much, Valentin and Constantin in particular. I really appreciate these talks.
Okay, bye.